Hello everyone, we are back and we are doing our quick tutorial on one-way ANOVA. Wait, what am I doing? So this is the practice problem that we did in class together as a group, not the one that you did as participation. So researchers were interested in the effect of previous crimes on the presumption of guilt. They randomly assigned 15 people, so this will be an important number. 15 people to one of 3 groups. This will also be an important number. So N, they're already telling us big N is 15 and K is equal to 3. Criminal record, clean record, or no information. Participants then read a news story about a crime that had been committed and who they suspected committed the crime. The news stories were the same except for the manipulation of information about the past crimes. After they read the story, they were asked to answer on a score of 1 to 10, innocent being 1, 10 being guilty, if they thought the suspect was actually committed a crime. The data is as follows. So remember, for ANOVA, we don't have to worry about one-way tests versus one-tailed test versus two-tailed tests. And so that's not something that's an important piece of information to pull out here. The number of total scores is, so that our big N is 15. Our number of groups is, our K is 3. With the data that's following, we can also see that our little n for each of these groups is equal to 5. These are going to be important pieces of information when we calculate our degrees of freedom. So, step 1, we're going to state the hypothesis in terms of the population. For ANOVA, because there's a whole bunch of different ways that there could be a difference, we're going to say there is at least one difference. And again, we want to make sure we're including what we're measuring and what we are manipulating so that we know kind of what we are talking about. And for our mathematical expression, again, because there are so many different ways that the null could not be accurate, we are just going to say not the null. In terms of our null hypothesis, that there are no differences. Again, we're going to have what we're measuring and what we're manipulating. For our null hypothesis, we're just going to make sure that all 3 of our groups are present here, that they're all equal to each other. If we were to ever do an ANOVA that had 4 groups, then we would just have the same thing, except we would need to have that 4th group there. So again, it's really just an issue of how many populations are you talking about, how many are getting included here to make sure that's accurate. Step 2, again, this is going to be an F distribution, is the shape. So this is the shape of our distribution or the kind of distribution. We have to say what kind of F distribution it is. What are we going to look up on our table? And remember, for ANOVA, we have 2 different degrees of freedom that we need to do. We're going to need to do our between treatments degrees of freedom. That's this value here. And we're going to need to do our within subjects degrees of freedom. Again, remember we pulled out from that information on the first page that big N was equal to 15 and K was equal to 3, the number of groups. And so for our between, we just say K3 minus 1 is equal to 2. For our degrees of freedom within, our big N of 15 minus that K is equal to our 12. Step 3, we're going to take this information that we just said. We're going to use an F table because it's an F distribution. We are going to use our degrees of freedom between that we just calculated as our degrees of freedom numerator, which is 2. Our within groups degrees of freedom will be our denominator, and that will be our degrees of freedom within. This is because in our final F, we're going to have mean squared between over mean squared within. And so again, we see this degrees of freedom will go into the calculation of mean squared between. This degrees of freedom will go into the calculation of mean squared within. And so this is why they're getting the titles numerator and denominator. So when we use our table, which I'll show you in a second, we would find our cutoff value at 0.05 is 3.88. If I were to ask you for 0.01, then we would have 6.93. And notice in this image here, we have the percentages marked for each of those cutoff values. So 3.88 is 5%, 6.91 is 1%. So again, here is our degrees of freedom, our F table using our degrees of freedom numerator and our degrees of freedom denominator. So again, we said our numerator was 2, our denominator was 12, and so the value that we are interested in is this 3.88. If we had been asked about 0.01, then that's where that 6.93 below is. Notice here that we have 0.05 is in regular faced print, and 0.01 is bold. So that's why there's those two numbers, and again, it's just which one is going to be 0.01 and which one's going to be 0.05. Step 4 is where the fun really starts. Again, this is where we're going to have the biggest changes to our 6-step process. Step 4 is still where we are going to calculate that test statistic, but now it's done in 3 sub-stages. Yay! More work! Really, the biggest one is 4A, where we're going to calculate these kind of new values that we haven't calculated before. In B, we don't actually need to calculate our mean squared total. We will calculate our mean squared between and our mean squared within, but that's just that tattooed formula that's on the on my forehead. Sums of squared divided by degrees of freedom for each of those sums of squared and each of those degrees of freedom. And so that isn't really that new because we've been doing that since chapter 4. And then that last stage will be compute our F statistic. So first we're going to start with our sums of squared within because these are skills that we've been doing all along. So our sums of squared within formula is going to be equal to the sum of the sums of squared in each treatment. So to do that, I'm going to need to calculate the sums of squared of each treatment. So for my criminal record group, I have these 5 scores. I add those 5 scores together and I'm going to get 40. I'm going to divide that by 5 and I get my mean of 8. This 40 will be our t value for our sums of squared between treatments. So that step before the mean is our t. T equals total. So what we're going to do is just our sums of squared for our criminal record group. So 10 minus 8, 7 minus 8, 5 minus 8, 10 minus 8, 8 minus 8 gives us these values. We're going to then square each of those values, which gives us these values. We add them all together, and we get our sums of squared for our criminal record group is equal to 18. We'll do the same thing, for our clean record group. Again, we'll add these values together. We will get 20 here when we add these values together. So our t is going to be 20, and our mean is equal to 20 divided by 5. That's how we got that value there. We're going to just subtract that across the board for our sums of squared. And we get these values. We're going to square each of those values. And we get these values. We'll add them all together, and we'll get our sums of squared for our clean group. Same thing for our last group, our no info group. We'll add those values together. We'll get a t is equal to 25. Our mean is equal to 25 divided by our little n, which is 5, which is where we get this value. We're going to subtract that from each of these scores, again, getting those deviation scores. And we get these values. We'll square each of those, and we get these values. We'll add them all together, and this is our sums of squared for our no info group. And then those values will be what we use to calculate our sums of squared within. Let's go ahead and get some other kinds of numbers that we're going to need for our degrees of freedom, our sums of squared between. Here are all those t's that we calculated previously before we got our mean. So here are those values that we already talked about. If we add all of those values together, we will get our G, which is the sum of all the t's. G just stands for our grand total. So if I added all of the scores together, all of these x values together, I get 85. The sum of x squared is taking, again, these raw values and just squaring each of them. And that's how I get these values. These are not our deviation scores. We are just squaring the individual values. And we get these. Right? And then we add them all together. So I chose to do them in each of their groups just to kind of organize my data better. But you can see that that's what we did here. So 388, 338, 338, 100, 100, 151, 151. We add all of that together and we get that 589 is the sum of each value squared added together. So all of those values that we just calculated are here on this sheet. So to calculate our sums of squared total, I'm going to do this one at the top. We had our 589, right? This value here. And we're going to subtract our G, our grand total, 85 squared divided by our big N is 15. We reduce that out, we get 589 minus 481.67. We do the math on that, and we get our sums of squared total is equal to 107.33. Now remember, you do not need to calculate every single one of these. You can just calculate two. And because of that kind of variance pi, everything will equal up to our sums of squared total. And we'll just figure out what kind of pi, what kind of pieces these sums of squared within and these sums of squared between are. So our sums of squared within treatment is literally just adding these three values together. So 18 plus 20 plus 26 is equal to 64. Let me make that a little clearer. 64. Okay, again, these are those sums of squared that we had calculated on those previous pages. And so now we know that our sums of squared within is 64. So I have two of those values now. I could just use algebra to get this third value to get our sums of squared between. I am going to go ahead and calculate our sums of squared between because it's a good way to check our work. So we have each of these t values that we calculated previously. Notice this part of the equation is the same as this part of the equation. So I can just take this number that I already calculated and I can pull it down here. So I don't have to redo that piece of it. This 85 squared over 15, which is what that was, and is equal to 15. And so I don't have to recalculate that. But I do need to do this first part. Again, the way this formula is written is it's saying the sum of this value. And then you subtract that. So we're going to do this part first, and then we'll subtract the other. So 40 squared over our little n, we had 5 numbers that went into that 40. So we will have 5. And then we're going to add our 20 squared. 5 numbers went into 20. And then we're going to add our 25. And 5 numbers went into that. So again, these are just each of these values going into this part here. And then we're going to subtract our 85 squared over 15. We start to reduce this out. We get 1600 divided by 5 plus 400 divided by 5 plus 625 divided by 5. We know this value, again, was 481.67 because we calculated it right here. So we can use that same value down here as well. We'll further reduce this out. So we have 320 plus 80 plus 125. Further reduce that, and we get 525 minus our 481.67. When we do that, we get a sums of squared between treatments of 43.33. Oops, sorry. Margins and all. And we can check our work and make sure that, in fact, our sums of squared between plus our sums of squared within is equal to our sums of squared total. And when we do that math, 43.33 plus 64 equals 107.33. So we have our whole pie together. And again, we can use this to check our work. This is the newest piece of the calculations. So after this is the brunt of the work. This is the, I'm done. And then we move on to the stuff that we're familiar with. So again, we'd already calculated 2 of these values, but we hadn't calculated our our degrees of freedom total. That's just our big n-1, the formulas that we've been using all along. But notice that we still have this kind of pie situation. We have degrees of freedom total, and part of that is our degrees of freedom between, and part of that is our degrees of freedom within. So once I had these 2 values, once I had our degrees of freedom within and our degrees of freedom between, I could just add 12 and 2 together and I will get 14. So again, it's the same situation with sums of squared. Step 4B, this is the stuff where we've got my tattooed forehead formula. So my formula on my forehead is sum squared divided by degrees of freedom. And so we're just going to, the important part here that is a little bit different is we need to make sure we are matching up our sums of squared between and our degrees of freedom between. And we're matching up our sums of squared within our degrees of freedom within. And so that's why those little sub-labels can be helpful. It just helps us keep track of this information. So our sums of squared between, we calculated at 43.33. Our degrees of freedom between, we calculated at 2. We will just divide those values. And here we had our sums of squared within as 64. Our degrees of freedom within is 12. We'll just divide those values. Oh, and I'm sorry, I did not have those divided for you. Why won't it go back? There we go. And so I will do that math for you here now. So our mean squared between then is going to be 21.67 when I do that math. My sums of squared within 64 divided by 12 will give me 5.33. And these are the 2 values that I'm going to take into my F. So my mean squared between divided by my mean squared within. So we said mean squared between was 21.67. We said mean squared within was 5.33. So we'll divide those values and we get an F of 4.07. And phew, we did it. We did step 4. It is a lot more labor intensive than a t-test. And so that's why you'll see, even though you can use ANOVA with 2 groups, most everybody's going to still do a t-test because it's a little bit more straightforward than an ANOVA. Step 5 and 6 are the same. So step 5, put that calculated statistic on our comparison distribution. And so we're going to be able to reject the null. Our value is in this critical region, right? So we're going to be able to reject the null and support our research hypothesis. An APA style finding here would again have what we manipulated. Our criminal record information made a difference. We don't know what kind of difference. We just know that there is a difference in our presumption of guilt. Our F statement here, the difference is we're going to need to include both of those degrees of freedom, whereas in our T statement, we only had to have that 1 degrees of freedom. We still are going to need a measure of effect size, and I will run that through you in just a minute. The last other thing that I want to remind you about is our ANOVA source table. So we just did a whole bunch of calculations and a whole bunch of work, and sometimes it's hard to organize all of that. And so these are the values from our ANOVA source, from all of the calculations that we just did, but we organize them in one space. And the beauty of the ANOVA source table is it really allows us to have all of this in one place, but also we can use these for our own calculations. So the way that this table works is we're going to, again, remember that we have these kind of pies. And so we can add those two columns together. So we can add 43.64 together, and we'll get 107.33. I can add 12 and 2 together, and I can get 14. So again, we have this additive relationship going down for our sums of squared and our degrees of freedom. Our mean squared, we can just divide across. And so here we would say 43 divided by 2 is equal to 21.67. 64 divided by 12 is equal to 5.33. Again, this can allow us to kind of organize our data in ways that makes a little bit more sense. And then the last piece, notice that we have our between conditions, above or within conditions. That's because I can just divide that is equal to our 4.07. Now on other blank source tables, I may not have had these boxes grayed out for you. You are welcome to gray those out for yourself. We do not need mean square total, and there are no other values for F. So please use this as a tool to help you kind of organize your data as well. The last thing that we need is our measure of effect size. Our measure of effect size here is eta squared. We get this by taking our sums of squared between treatments. Again, we calculated that as 4.33. Our sums of squared total, which we calculated as 107.33, we'll just divide those, and we get our eta squared of 0.04. If we were to, if we were to go back, then we can put our eta squared here as that value here. And so you could put your measure of effect size. The only other thing that sometimes gets included in this APA style statement is right here. You'll see people include mean squared error, which is whatever that denominator is. It's your error term. Remember, we've been talking about that all along. So this would be our mean squared within here. And the reason people would include that value, which again here is 5.33, is because if I have that value, I'll have this for my F statement, I'll have this for my F statement, I'll have this for my F statement, and I'll have this for my F statement. And that allows me to calculate everything back. So then if I have both of these degrees of freedom, I can get this value. If I have these two values, I can get this value. If I have these two values, I can get this value. If I have these two values, I can get this value. And once I have these two, I can get this. So again, by including that mean squared within value here in that F statement, it is not required, but I will give you 2 bonus points for doing it on your homework because it does allow us to really build back this ANOVA source table in really helpful ways. So that ends our quick tutorial on, wait, what am I doing? I hope this was helpful.